Hello, my precious friends. I really hope that you are doing great. Welcome to our today's class. It is our seventh lesson on the third topic of Form 4, which is called floating and sinking. As usual, let me commence by giving the quote of the day, which states that nobody cares about your story until you win. We shall discuss that quote at the end of our class today. So today we are looking at Archimedes' principle and moments. So let's start by looking at an example, which reads that the figure below shows a block X that weighs 2 Newton in air and has a density of 2.0 grams per cubic centimeter. If the bar is pivoted at its center and is in equilibrium, find the distance y. Then you are told to take the density of water as 1 gram per cubic centimeter, which is always equivalent to 1000 kilogram per cubic meter. So for us to compute the distance y, we must have all the forces that are acting on this particular bar in order to keep it in equilibrium. So one of the forces you are given as 1.2 Newton. Then of course the other force will be due to the weight of this particular block. But because the block is placed in water, we shall have the upthrust acting in the upward direction. Therefore, the difference between the weight of the block X in air and the upthrust will be the tension acting in this particular string, which is equivalent to the apparent weight of that particular block. Therefore, the force that we'll use here will be the apparent that is the apparent weight of the block, because the apparent weight is the difference between the weight of this particular block and the upthrust. So for us to find the apparent weight of the block, we need to have the weight of the block in air. Then we subtract with the upthrust of that particular block in water. So the weight of the block in air we are given as 2 Newton. Therefore, we need to compute the upthrust of that particular block when it is placed in water. Then from Archimedes' principle, we know that upthrust must be equal to the weight of the fluid displaced. Of course, the fluid being displaced in this case is water. Therefore, the upthrust force will simply be equal to the weight of the water that will be displaced. For us to find the weight of the water displaced, we need to have the density of the water displaced. We also need to have the volume of water displaced and the gravity. So the density of the water that was displaced, we are given as 1 gram per cubic centimeter. So the only unknown that we have is the volume of the water displaced. And because the block X was totally immersed in water, it simply means that the volume of the water displaced will be equal to the volume of the block X. Therefore, let's start by finding the volume of the block X. So to find the volume, you need to have the mass and the density. So because you are given that the block X weighs 2 Newton in air, that is the true weight of that particular block X. Therefore, we know that weight is equals to mass times gravity. So weight of the block X will be equal to the mass of the block X multiplied by the gravity. So the weight is 2 Newton in air is equals to the mass of the block multiplied by the gravity, which is 10 Newton per kilogram. Therefore, the mass of block X will be given by the weight, which is 2 Newton, divided by the gravity, which is 10 Newton per kilogram, which gives us the mass of block X as 0.2 kg. Now that we have the mass of block X, we can easily find the volume of block X, because we know that volume is equals to mass over density. Therefore, volume of block X will be equal to the mass of block X divided by the density of block X. So the mass of block X is 0.2 kg divided by the density of block X. We are given from the question as 2 gram per cubic centimeter, but we know that 1000 kilogram per cubic meter is equals to 1 gram per cubic centimeter. What about 2 grams per cubic centimeter? So that will be 2 grams per cubic centimeter over 1 gram per cubic centimeter multiplied by 1000 kilogram per cubic meter. So we are converting to kilogram per cubic meter because those are the SI units of density. So 0.2 kg divided by 2 times 1000, you'll obtain the volume of the block X as 0.0001 cubic meter. Then because the block X was totally immersed in water, it simply means that the volume of block X will be equal to the volume of the water that was displaced as a result of placing the block X in water. Therefore, we shall say that the water, that is the weight of the water displaced, will be equal to density of water displaced times volume times gravity. But we know that the volume of water displaced will be equal to the volume of the block X, because remember the block X was totally immersed in water. So it simply means that the volume of water that it displaced will be equal to the volume of that particular block X. Therefore, the volume of block X will be equal to the volume of the water displaced. Therefore, the weight of the water displaced will be equal to the density of water displaced times volume of the block multiplied by gravity. Density of water displaced, of course, the density of fresh water is usually 1 gram per cubic centimeter, which is equivalent to 1000 kilogram per cubic meter, which is the SI unit for density. Then the volume of the block, of course, you have already computed it as 0.001 cubic meter. Then gravity is 10 Newton per kilogram. So 1000 times 0.0001 multiplied by 10, you will obtain the weight of the water displaced as being 1 Newton. Then from the Archimedes principle, which stated that when a body is partially or totally immersed in a fluid, it experiences an upthrust equal to the weight of the fluid displaced. It simply means that the upthrust force will be equal to the weight of the fluid displaced. Of course, the fluid being displaced in this case is water. Therefore, upthrust will be equal to the weight of the water displaced, which we have already computed here as 1 Newton. Now that we have the upthrust, we can easily find the apparent weight of the block X, because that will be actually the tension in this particular string. So the apparent weight of the block X is equals to the weight of the block X in air minus the upthrust in water, because it was immersed in water. So weight in air we are already given from the question as 2 Newton, minus the upthrust in water, we have computed it as 1 Newton. Therefore, 2 Newton minus 1 Newton will obtain 1 Newton. So that is the apparent weight of the block X, which will be actually the force acting in this particular string. So remember, the force in this string is the difference between the true weight of block X and the upthrust, which is called the apparent weight of that particular block X. Now that we have the force in this particular string, then we also have the force in this other string, we can easily apply the principle of moments, which actually stated that for a system in equilibrium, the sum of clockwise moments must be equal to, that is, for a system in equilibrium, the sum of clockwise moments at a point must be equal to the sum of anti-clockwise moments about the same point, that is measured from the pivot. So F1 D1 must be equal to F2 D2. So F1 D1 represents the clockwise moments, which are the forces that will cause this bar to rotate in the clockwise direction, or in a direction similar to that of the clock that is in relation to the pivot. So this will be the apparent weight here will be the clockwise moment, which is F1 D1. So the force F1 is the apparent weight, which you have already computed it as 1 Newton. Therefore, F1 is 1 Newton. Then the perpendicular distance of the apparent weight from the pivot is 24 centimeters. So in meters, we'll simply take 24 over 100, which will give us 0.24 meters. Then anti-clockwise moment are the forces that causes the bar to rotate in the anti-clockwise direction, or in a direction opposite to that of a clock that is relative to the pivot. For example, the 1.2 Newton force will cause the bar to rotate in this direction, which is the anti-clockwise direction. Therefore, 1.2 Newton would contribute to anti-clockwise moments. So F2 will be 1.2 Newton multiplied by the perpendicular distance of F2 from the pivot, which is y. So 1.2 multiplied by y. So if I make y the subject of the formula, I'll simply have 1 Newton multiplied by 0.24 meters divided by 1.2 Newton. So because I've expressed everything in SI unit, so I expect also the value of y to be in SI unit of length, which is actually the meters. So 1 multiplied by 0.24, you just obtain 0.24. 0.24 divided by 1.2, you'll obtain 0.2 meters. Or in centimeters, if you multiply by 100, you'll obtain 20 centimeters. Therefore, the distance y is 0.2 meters or 20 centimeters. Next, we look at our second example, which reads that the figure below shows a block of mass 50 gram and density 2000 kilogram per cubic meter submerged in a certain liquid and suspended from a uniform horizontal beam using a string. So a mass of 40 grams suspended from the other end of the beam puts the system in equilibrium. So determine part A, the upthrust force acting on the 50 gram block. So because the system is in equilibrium, it simply means we can apply the principle of moments. So part A, they want us to find the upthrust force acting on the 50 gram block. For us to find the upthrust force, we must first of all have the apparent weight acting through this particular string, because the apparent weight will be the force that is contributing to the sum of anti-clockwise moments. So from the principle of moments, the sum of clockwise moments must be equal to the sum of anti-clockwise moments. That is about the same pivot. Then of course, if the system is in equilibrium. So F1 and D1 would represent the sum of our clockwise moments, which of course will be the force due to the 40-gram mass and the perpendicular distance of 20 centimeters from this particular pivot. So our force F1 will be, we convert the 40 grams into a force. So we know that force is equals to mg. So the mass is 40 grams. To change into SI unit, we divide by 1000 times 10 to convert that is to find the weight, or the force due to 40-gram mass will be equal to the weight of the 40-gram mass, which is equal to mg. So the 40 grams over 1000 to convert it into kg, then of course times 10 Newton per kilogram to find the weight. Then D1 is the perpendicular distance of the 40-gram mass, that is mass from the pivot. So the 20 centimeter, the distance of the 40-gram mass from the pivot is 20 centimeters in SI unit, which is the meter. I'll take 20 centimeter over 100 centimeter times 1 meter. Then F2 D2, so the F2 will be the apparent weight. So the force that will be felt in this particular string will be the difference between the upthrust and the weight of the 50-gram mass, which is called the apparent weight. So it will be the apparent weight multiplied by the perpendicular distance of the 50-gram mass from the pivot, which is 32 centimeters. To convert into meters, I'll take 32 over 100 to convert it into meters. So let's first of all find the apparent weight due to the 50-gram mass in this particular liquid. So if you take 40 over 1000 times 10 times 20 over 100, you'll obtain 0.08. Then 32 over 100, you'll obtain 0.32 multiplied by the apparent weight. Therefore, the apparent weight will be equal to 0.08 divided by 0.32, which gives us 0.25 Newton. So for us to find the upthrust, because the question wants us to find the upthrust force acting on the 50-gram mass, so we know that upthrust is equals to the weight in air minus the apparent weight. So the upthrust due to the 50-gram mass being immersed in the liquid will be equal to the weight of the 50-gram mass minus the apparent weight due to the 50-gram mass in this particular liquid. So the weight of the 50-gram mass, of course, is given by mg, so minus the apparent weight. So mg, the mass of the 50-gram mass, is of course 50 gram over 1000 to convert to kg times 10 to find its weight, which is equal to the force. Then the apparent weight, we have already computed it as 0.25 Newton. So if you take 50 over 1000 multiplied by 10, you'll obtain 0.5 Newton, then minus the apparent weight, which is 0.25 Newton. So 0.5 minus 0.25, you'll obtain the upthrust force due to the 50-gram mass in the liquid to be 0.25 Newton. Then Roman 2, they want us to find the density of the liquid. So in order for us to find the density of the liquid, we must first of all have the weight of that particular liquid that was displaced. And remember, from the Archimedes principle, upthrust must be equal to the weight of the liquid displaced. So upthrust is equals to weight of the liquid displaced. So the upthrust, of course, due to the 50-gram mass is 0.25 Newton, which we have computed from Roman 1, which must give us the, remember, the weight can be given by rho Vg, that is density of the liquid displaced times volume of the liquid displaced times gravity. But because we don't have the volume of the liquid displaced, but we know that because the 50-gram mass, it was totally immersed in the liquid, it simply means that the volume of the liquid displaced due to immersing the 50-gram mass in the liquid will be equal to the volume of that particular 50-gram mass or the block. Therefore, volume of the liquid displaced is equal to the volume of the block, because the block was totally immersed in the liquid. Therefore, the liquid that it displaces must be equal to the volume of that particular block, then of course times gravity. So again, we don't have the volume of the block, but we know that volume can be given by mass over density. Therefore, the volume of the block will be equal to the mass of the block divided by the density of the block. Therefore, upthrust, which is 0.25 Newton, will be equal to the density of the liquid displaced times the volume of the liquid displaced, which is equals to mass of the block over the density of the block multiplied by gravity. So 0.25 Newton is equals to density of the liquid displaced multiplied by the mass of the block, of course, in that is in SI units. So the mass of the block was 50 gram. So to convert into kilogram, I'll simply take 50 divided by 1000 to convert into the SI unit, which is the kilogram. Then divided by the density of the block. We were given from the question that the 50 gram block has a density of 2000 kilogram per cubic meter. So the density is 2000 kilogram per cubic meter, then of course times 10. So 50 divided by 1000, you'll obtain 0.05 kg, which is the SI unit for the mass. Then of course divided by the density of 2000 kilogram per cubic meter, so that we find the volume. So 0.25 Newton will be equal to, if you take 0.05 divided by 2000 multiplied by 10, you'll obtain 0.00025, of course, Newton cubic meter per kg. Therefore, if I make density of the liquid displaced subject of the formula, I'll simply have density of the liquid displaced being equal to 0.25 Newton divided by 0.00025 Newton cubic meter per kilogram. So if you take 0.5 divided by 0.0025, you'll obtain 1000 kilogram per cubic meter to be the density of this particular liquid that was displaced by the 50 gram mass block. Next, we look at Roman 3 of our second example, which reads that calculate the new balance point of the 50 gram mass from the pivot. Then we are told that the 40 gram mass remains fixed, which means that this particular distance of 20 centimeters does not change if the liquid was replaced with one whose density was 1500 kilogram per cubic meter. So the only thing that changed, we replaced the old liquid with another new liquid which has a density of 1500 kilogram per cubic meter. So if we are replacing with a liquid of a different density, it simply means that the apparent weight felt in this particular string will also change. Therefore, we need to find the new value of the apparent weight. Then we know that apparent weight will be given by the weight of the 50 gram mass in air minus the upthrust. So in order for us to find the apparent weight, we need the value of the new upthrust and of course the weight of that particular 50 gram mass in air. So let's start by computing the new upthrust due to the new liquid. So remember, different liquids will offer different values of the upthrust force. So the new upthrust force will be equal to the weight of the new liquid that is displaced. Remember from Archimedes' principle that when a body is partially or totally immersed in a fluid, it experiences an upthrust equal to the weight of the fluid displaced. Therefore, the upthrust must be equal to the weight of the new liquid that is displaced. So the new upthrust will be equal to weight of the liquid displaced will be given by rho Vg, that is density of the new liquid displaced multiplied by the volume of the new liquid displaced multiplied by gravity. Then because the 50 gram mass was totally immersed in the new liquid, it simply means that the volume of the 50 gram mass will be equal to the volume of the new liquid that will be displaced. Therefore, the volume of the new liquid displaced will be equal to the volume of the block because the block is totally immersed in that particular liquid. Remember, volume is the amount of space occupied by a body. Therefore, the 50 gram mass, the space that it occupies will just be equal to the space that has been left by the new liquid displaced. That is why we are saying that the volume of the new liquid displaced will be equal to the volume of the block because the block was totally immersed in that particular new liquid. But you know that volume is given by mass over density because remember from Roman 1 and 2 we were given the mass of the block, we were also given the density of the block as 2000 kilogram per cubic meter. Therefore, the new upthrust force will be equal to the density of the new liquid displaced multiplied by mass of the block over density of the block multiplied by gravity. Remember, mass over density of the block will simply be equal to the volume of the new liquid displaced. So density of the new liquid displaced, the new liquid has a density of 1500 kilogram per cubic meter. The mass of the block was 50 grams, that is from our Roman 1. Then the density of the block was 2000 kilogram per cubic meter, then of course times 10. So to convert the 50 gram into SI unit, which is the kilogram, I'll simply take 50 divided by 1000, which will give me 0.05 kg, which are the SI units for mass. Therefore, 1500 multiplied by 0.05 divided by the density of the block, which is 2000 multiplied by 10, I'll obtain 0.375 Newton as the new upthrust. Remember, each liquid has its own value of the upthrust. Therefore, the upthrust due to the new liquid will be equal to 0.375 Newton. Therefore, the new apparent weight that will be felt in this particular string will be given by the weight of the 50 gram mass minus the new upthrust. So the weight of the 50 gram mass, of course, is given by mg minus the new upthrust. So because the 50 gram mass has a mass of 50 gram, to convert to SI unit, I'll divide by 1000 multiplied by 10, then minus the new upthrust due to the new liquid, which is 0.375 Newton. So 50 over 1000 by 10, you'll obtain 0.5 Newton minus the new upthrust is 0.375 Newton. So 0.5 minus 0.375 Newton, you'll obtain 0.125 Newton. So that is our new apparent weight. So remember, when you are calculating using the principle of moments, what we use in calculation is the apparent weight, because that is what is felt at this particular point. That is the difference between the weight of the 50 gram mass and, of course, the upthrust. Remember, the upthrust is acting upward while the weight is acting downward. So the difference is the apparent weight, which will be felt in this particular string. Now that we have this force and, of course, this distance and also the 40 gram mass, we can now easily apply the principle of moments because the system is in equilibrium. So I'll take the clockwise moments will be F1 times D1. So this force will cause this bar to rotate in the downward direction, which is in the direction of the clock. Hence, it will contribute to clockwise moments. Therefore, F1 D1. So the force due to the 40 gram mass will be 40 gram. Remember, force is mg, so it will be 40 over 1000 to convert the mass into kg, multiplied by 10 to convert it into a force or the weight. Then D2 is the perpendicular distance of the 40 gram mass from the pivot, which is 20 centimeters, in SI unit, which is the meter. I'll divide by 100. Then F2, of course, will be the apparent weight at this particular point, which we have computed as 0.125 Newton. So the apparent weight, 0.52 Newton, times the perpendicular distance of the 0.52 Newton from the pivot. Of course, I've given it a letter as x, so 0.125 times x. So 40 over 1000 times 10 times 20 over 100, you'll obtain 0.08, which is equals to 0.125 x. So the value of x will be given by 0.08 divided by 0.125, which gives us 0.64 meters, which converted to centimeter, it will give us 64 centimeters. Therefore, the distance x will be 0.16 meters or 64 centimeters. Lastly, I have an exercise that I recommend you should try at your own free time to get the understanding of the concept that you have just learned. Of course, if you have any challenges in handling any of the questions, feel free to drop a comment specifying the question that you need help in. And as usual, I'm always here to try and help where possible. So we've come to the end of our class today, but we need to discuss the quote of the day. The quote of the day stated that nobody cares about your story until you win. So the quote is warning us against expecting everyone to support us whenever we are still on the journey of pursuing our greatness. It is also reminding us that achieving greatness is never an easy task. We must therefore be determined and disciplined in everything we do if we want to be truly successful. And lastly, recall that every great person has a sad story that led them to their greatness. Therefore, do not give up whenever you encounter challenges on your way to greatness. Thank you very much for accompanying me until the end of this particular lesson. I do not take it for granted. In case you are new to the channel, kindly hit the subscription button and also turn on the notification bell so that whenever I upload a new video, you will get notified. Until next time, this is Kind Tuition Academy. Thank you very much.